Somewhere in the south of France, there is a highway that appears to float. On certain mornings, a thick blanket of fog settles into the valley below, and the cars crossing it seem to be driving on nothing at all, suspended above a silent sea of clouds. Beneath that white ocean lies a drop of nearly 900 feet. This is the Millau Viaduct, and it is the tallest bridge ever built by human hands. Its highest point climbs 343 meters into the sky, which means this single structure stands taller than the Eiffel Tower. But the story of how it was built is far stranger than its height. Because to construct it, engineers had to solve a problem that ordinary machines simply could not touch. They had to move 36,000 tons of steel out across an open void and let it hang in midair. To understand why this bridge exists, you have to understand the valley it crosses. For decades, the town of Millau was a bottleneck. The main route connecting Paris to the Mediterranean coast plunged down one side of the Tarn River valley, crawled through the town below, and climbed painfully up the other side. Every summer, hundreds of thousands of vacationers funneled into this single choke point, and the traffic could stretch back for miles. The obvious answer was to leap straight over the valley. But the Tarn Valley is not a gentle dip in the landscape. It is a vast, deep gorge, and it is haunted by wind. Powerful, unpredictable gusts sweep through the gap, accelerating as they are squeezed between the plateaus. Any structure built here would have to stand nearly 1,000 feet tall and survive being battered by some of the most violent crosswinds in France. The first challenge was the piers. 7 concrete columns would have to rise from the valley floor to carry the roadway, and the tallest of them would climb to 245 meters of solid concrete before the mast on top even began. At that scale, the smallest error becomes catastrophic. If a pier leaned even slightly off vertical near its base, that tiny deviation would multiply into meters of error by the time it reached the top. So the engineers used climbing formwork, a mold that slowly ratcheted itself upward as each new section of concrete cured beneath it. Guiding this process was a network of receivers locked onto GPS satellites orbiting the Earth, constantly checking the exact position of the forms. Layer by layer, the concrete rose with a precision measured in millimeters, each pier tapering elegantly as it climbed, then splitting near the top into a slender fork to cradle the deck. It was patient, relentless, and almost perfectly vertical. But the piers were only half the puzzle. The real nightmare was the deck. The roadway of the Millau Viaduct is a continuous ribbon of steel, more than 2,400 meters long. In a normal bridge project, you would lift the deck segments into place using cranes. But here, that was impossible. No crane on Earth could reach nearly 900 feet into the air to set steel down onto the tops of those piers. And even if one could, hoisting thousands of tons of roadway into the sky, section by section, over a wind-swept gorge would have been agonizingly slow and dangerous. The engineers needed another way entirely. They needed to build the bridge without ever lifting it from above. The solution was as elegant as it was audacious. Instead of assembling the deck in the sky, they assembled it on solid ground. On the flat plateaus at each edge of the valley, workers welded together enormous sections of the steel roadway, building the deck backward from the cliff edge. Then, once a section was ready, they pushed it. Using a system of computer-controlled hydraulic rams, the entire steel structure was slid forward, inch by inch, out over the edge of the valley and into open air. This technique is called incremental launching, and at Millau, it was performed on a scale never attempted before. Picture it. 36,000 tons of steel, creeping forward off the edge of a cliff, cantilevering out into nothing. The hydraulic system worked in tiny, deliberate strokes, advancing the deck roughly 60 centimeters at a time, then resetting its grip and pushing again. The deck moved at a crawl, only a few meters an hour, so slow you could barely see it happen. To stop the steel from sagging under its own weight across those enormous gaps, engineers installed temporary metal towers between the permanent piers, cutting each span in half during the launch. And at the very front, a lightweight steel nose reached ahead of the deck, feeling for the next pier and guiding the whole assembly toward its target. The two halves of the bridge, one launched from the north, one from the south, marched slowly toward each other across the valley. Everything depended on them meeting perfectly in the middle. After months of pushing, across a gorge nearly a mile and a half wide, the two steel arms finally reached the center. The alignment was almost flawless. The gap closed to within centimeters. Two ribbons of steel, launched from opposite cliffs and suspended over an abyss, had found each other in midair. Then, with the deck in place and the cables strung down from the masts to hold it, one final enemy remained: the wind. At that height, an unprotected crosswind could shove a high-sided truck sideways, or worse. So, along both edges of the roadway, engineers fitted transparent windscreens, nearly 3 meters tall, angled and shaped to break the force of the gusts. These barriers slice the wind speed, hitting vehicles roughly in half, taming the gale into something a driver can handle, while staying clear enough that the view across the valley remains breathtaking. Today, the Millau Viaduct stands as one of the great triumphs of modern engineering. It is not just tall. It is a demonstration of what becomes possible when human ingenuity refuses to accept that a problem is simply too big. A valley too deep to bridge, a deck too high to lift, a wind too fierce to ignore. All of it solved not with brute force, but with patience, physics, and nerve. A highway floating above the clouds where none should ever have been able to exist. If you enjoyed this deep dive into one of the world's most audacious structures, take a moment to subscribe to The Engineering Edge and stay with us as we explore the incredible feats of engineering that shape the world around us.